Welcome, this is Coach Dorf. Today we're going to do a review for the final exam. Now, the first thing I suggest you do is go to the Canvas course website and look under the review for the final exam. And in there, you should see a document that looks like this, Coach Dorf's study guide for the final exam. And here I list the major topics for the final exam. There are 16 topics here. You should know how to do each of these. These are the topics that are the most important ones. These are the ones that most often appear on the final exam. You can read through these. There's a definition of the derivative. We'll talk a little bit about some examples of these things. The derivative is rate of change, derivative, basic rules for derivatives, product quotient rules, and so forth. You can see all of those. After this, there is a list of 8 or 9 additional topics here. Could be on the final exam. They're not as common. They're not as important as the previous list, but they could appear. So you should know how to do these problems too. But if you only have time to focus on one thing, I would focus on the original list of major topics and then look at the additional topics. All right. Again, I would expect that most of these things in the major topics will appear on the exam, but not all of them. And some of these on the additional topics what may appear, but not all of them either. So again, focus on the major topics and then look at the additional topics. In the study guide, I give some examples and I want to go over how to do some of these examples. All right, so the first one is use the definition of the derivative. Now, I've mentioned in class that this is something you definitely should know. If I look up the previous final exams, almost every final exam, if not every final exam, has one of these types of problems. All right, and it's to use the definition of derivative. You're given a particular function and you're supposed to find its derivative. Well, let me just do x squared plus 1. What I would like you to do now is to stop your video and write down what is the definition of the derivative. I'm going to show it to you in a second so you can check yourself on this. Okay, welcome back. Let me show you, you've now written down your own definition of the derivative. Let me show you what it is, and you can compare this. There are 2 of them. I'm going to focus on the more common one. The limit as h goes to 0 of f of x plus h minus f of x all over h. All right, there's the definition of the derivative. Now I'm going to apply this to my particular function, which is this. So I'm going to get the limit as h goes to 0, and I'm going to take my red function and plug it in to here first. So when I do that, I have x plus h quantity squared plus 1. That is my f of x plus h. Then my next step is to take f of x and plug it in. So I'm going to just plug this one in now over here. So here's my f of x. It's x squared plus 1. And this is all over h, all right, which comes from this part here. All right, now I'm going to have to simplify a little bit. Notice as I'm doing this, I'm always writing down my limit. I can't just stop writing down the limit. I need to include that. So I have the limit as h goes to 0 still. And now I'm going to simplify what is in this part here. So what is that going to be? That's going to be x plus x squared plus 2xh plus h squared plus 1. So you may ask, where did I get that x squared plus 2x h plus h squared? Well, if I do x plus h squared, that's x plus h times x plus h, and that's going to equal, by the FOIL method, x squared plus xh plus hx, which is the same thing as xh, plus x squared. And the 2 terms in the middle are the same, so I can write 2xh plus h squared. Okay, so that's where I get that from. And then I'm going to keep writing down my x squared plus 1 here and h. Notice that I am using the square brackets here because I want to keep them separated, because in the middle there, I've got a minus. And I need to remember to distribute that to both terms here. So when I write that out, I'm going to have the limit as h goes to 0 of x squared plus 2xh plus h squared plus 1. And then I have a minus x squared and minus 1 there, right? Make sure you get that minus 1 there because you've got that minus in front of the square bracket of the last term there. All right, and then that's all over h. And then I notice that I have some things in common. This x squared and this negative x squared cancel out, and this 1 and this negative 1 cancel out. That should happen. That's a good thing. So then I have the limit as h goes to 0 of 2xh plus h squared all over h. Now notice that at this step that everything in the top has an H in it and the bottom has an H in it. This is what you should have. If you don't have all the terms have an H in it in the top, then you've done something wrong and you go back and check it. Most common mistake at that point is that you forgot to distribute this negative that here I write in a circle in blue to both of these terms. That gives me these two negatives, which cancel out with the things in the beginning. All right. So I have those two H's. I have the H's, everything in the top with an H. So I'm going to factor that out. And that gives me an H. And then I put parentheses, 2x plus H all over H. And this is what we want. Okay. I have my H going to 0. So I should have an H on the top and an H in the bottom, where the H on the top is multiplied by something. And because of that, then I can cancel the h's out, which is a good thing. And then I have the limit as h goes to 0 of 2x plus h over 1. Okay, but I can leave that 1 off, but we'll just leave it there now. And now as h goes to 0, what happens? As h goes to 0, this goes to 0. And so I've now put the h in as 0. I've used the substitution method, and I'm just left with 2h. And now, does this make sense? Remember, my original function was h squared, f of x equals x squared plus 1. And you know by the shortcut rules that the derivative of that is 2x. So we did it right. Now let's go on to a second type of problem. Remember that the derivative represents three different types of ways of thinking. So one way is it's the slope of the tangent line. And we drew this out like if I had a little diagram here, and suppose this is my function, y equals f of x. All right, and if I take some point on there, let's just say, here's my x value. If I do the tangent line there at that point of f of x, so that point there is f of x because I have x, and then I go up here, that's my f of x. And the slope of this equals the derivative at that point, x. Another thing is it can be thought of as a rate of change. So how fast something changes instantaneously. And then the third one is if my function, I'll just call it s of t, where t is time, if this equals like distance or position, then the derivative of that we could write as v of t is velocity. So the derivative of distance is velocity. And if I did the second derivative, which would be the derivative of v, sorry, which would be a, which is acceleration. So I have distance, velocity, and acceleration. So those are the three most common ideas related to the derivative as the rate of the change. Now, let me give you a example of using rate of change here. Suppose you have a pot of water and it's at room temperature. And let's say you start boiling that water. We'll call T of t equals the temp at time little t. What happens to the derivative? So d capital T over dt. So how's the temperature changing with time? You're increasing the temperature of it because you're boiling it. So that means dt over dt is increasing. It's increasing or it's positive. It's getting larger, so it's going up. The temperature is going up. Is dt over dt constant? If I look at a small part of it, it probably is kind of constant. But if I look at over the long-term time, it's not going to be. You can't keep increasing it 1,000 degrees or 10,000 degrees or 1,000,000 degrees. Same thing, what if I took a pot of water now and I put it in the freezer? What's going to happen to it there? Well, it's going from a warmer situation to a colder one. So dt is decreasing and dt is negative because it's decreasing. All right. Can that be constant? No. it can only get so cold in the freezer. As soon as the temperature of the water matches the temperature in the freezer, it's not going to get any colder. All right, so it's not constant. Number three, let me give you a couple examples here. The log of the square root of x plus 1, and that is y. So what is the derivative of that? Well, so y prime is going to equal, the derivative of a log function is I take what's inside and I put it in the denominator. And then over in the numerator, I take the derivative of what's inside. So what do I have in the numerator? X to the 1/2 is x, the square root of x is the same as x to the 1/2. So I have this. I'm not going to change the denominator because I don't have to change, I don't have to take the derivative of the square root of x plus 1 in the denominator, only in the numerator. All right. And then by the power rule, I get that the derivative of this is 1/2 x to the negative 1/2. That's the power rule. I I take the exponent, I bring it out front, and then I reduce the exponent by 1. So 1/2 minus 1 is negative 1/2. And then I have the derivative of this, which is 0. So plus 0 over this. And now let's just do some simplification here. The numerator, this part here, is going to equal 1/2 1 over x to the positive 1/2 all over the square root of x plus 1. And that's the same thing as 1/2 1 over square root of x all over square root of x plus 1. Okay. And maybe you want to simplify that. That could also be written in some of the following forms. I could put the 1/2 out front and get this. Another thing I could do if I wanted to, I could multiply top and bottom by the square root of x. Why would I want to do that in the top? Well, in the top, then this and this are going to cancel out, and I would just get a 1. So I have my 1/2 out front, and then the numerator becomes 1. And in the bottom, the denominator, the square root of x times square root of x, this gives me x, and the square root of x plus 1 would give me this. So all those answers, this one's right, this one's right, this one's right, but any of them could be written there. Okay. Um, Product rules and quotient rules here. So what's an example product and quotient rule? Let's just do this one that's in the notes here in the study guide. So I have f of x equals g of x over x. G of 2 is 8. G prime of 2 is 3. And you're supposed to find f prime of 2. So we have to remember the quotient rule because this is a quotient, right? I have g of x in the numerator and I have x in the denominator. So that's a quotient. And the quotient rule says that if I have just any function, let's say g of x over h of x, then the derivative of all that, all right, d dx of that is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. That's the quotient rule. Remember the order here. It's the bottom times the derivative of the top. I see students sometimes make the mistake of doing the top times the derivative of the bottom first. Don't do that. It's the bottom times the derivative of the top. And then remember this is a minus there. And then you switch the order after that and you have the top times the derivative of the bottom. Okay, so let's apply that to this particular case. So what is the derivative of f? Remembering f is here, okay, g over x. So it's the bottom, x, times the derivative of the top, so g prime of x, minus the top, g of x, times the derivative of x all over the denominator squared. Now, don't get confused that here I wrote the derivative of g as g prime of x. That's perfectly fine. And here I wrote the derivative of x as d dx of x. Both of those mean the same thing. All right, so let's simplify it then. I have x g prime of x minus g prime. And then what is the derivative of x? Well, the derivative of x is just 1 by the power rule. So this gets times 1 times 1 all over x squared. And now we were supposed to find g prime of 2. So now I plug in 2. Well, you may say, well, they didn't give me the value of x. Well, okay, they didn't specifically say that x is 2, but here, this means that x equals 2. So I'm going to put that in here. Where I have this, I'm going to put in a 2. So there's the 2. And then I have g prime of 2 minus g of 2, where I'm using now this here. There's g. I'm putting in 2 for x. Okay, times 1 all over 2 squared, where I'm putting in 2 here for this x. Okay, then what is g prime of 2? Well, g prime of 2 was given up here as 3, so we're going to put in 3. I'll start using different colors here. And then I have a minus, and then I need g of 2. Well, g of 2 is right here, that's 8. So I'm going to put that in right here. So this is 8 times 1 all over 2 squared. We go back to black. So I get 6 minus 8 over 2 squared is 4. And so that gives me negative 2 over 4, or negative 1/2. All right. You should know both the quotient rule and the product rule. And this is a good example of this. Okay, so let's go to the next one. Um, this is topic number 5. It's the chain rule. We're going to differentiate f of x equals the square root of 3x squared minus 4. Okay, so how do I do this one here? Well, anytime I've got a square root, I want to write that as an exponent instead of having a square root symbol. So we're going to start as f of x equals parentheses or square bracket, whatever you prefer, 3x squared minus 4 to the 1/2 power. And now when I take the derivative of this, I think of this as kind of being like a big box to the 1/2 power. And the derivative of that is going to be by the power rule. I take the 1/2, bring it out front. Then I have the big box. I subtract 1 from the exponent, and so I get 1 minus a half minus 1, okay, or negative 1/2 here. And then I have to take the derivative of the inside, which is what the chain rule says. So applying that to here to this, what I'm going to get is a 1/2, because I'm bringing the 1/2 out front. Then I write what I have inside the square bracket. I reduce the exponent by a half, so I get a half minus 1, which is minus a half. And then I have the derivative of what's inside the square bracket. All right, and so now I keep doing this. So I have 1/2 square bracket, 3x squared minus 4 to the negative 1/2. And now I have to take the derivative of the 3x squared minus 4 here, and that's going to be 6x by the power rule. And now so that's a perfectly fine answer, but sometimes the answer will be cleaned up a little bit. So I'm going to have a 6x in the numerator, and then I have a 2 in the denominator uh, from this. So that's the 2 there. And what happens to this part? Well, that's the same thing as 1 over that to the positive half power. So negative 1/2 power is the same as 1 over that to the positive 1/2 power. Okay, the the 6 and the 2 reduce to be 3, and then I have an x, and then I can write this 1/2 as a square root. So when I do that, I'm going to get square root of 3x squared minus 4. And I think this would probably be a more common answer that I would see on an exam. Let me go on to a related rate problem here. Let me give you a different example that's in the study guide. So you can have two examples to look at. Look at the one in the study guide, but also then look at this one that I'm going to give you here. Radius of a sphere. A sphere is increasing at a rate of 2 centimeters a minute. At what rate is the surface area of the ball increasing when the radius is 8 centimeters? Draw a picture of this. So I have a ball, a sphere. We're given that the radius is increasing. So if something is increasing with time, that's going to be a d dr dt in this case, dr dt, and that's going to be 2 centimeters per minute. All right. And then they ask, at what rate is the surface area of the ball increasing? So we need a formula for the surface area of the ball. The surface area is 4 pi r squared. Now, this is a formula that I would think they would give you. I want to find the rate of change of S of r. So I want to find the rate of change. So I'm going to look at d dt of that, and I'm going to look at d dt of the right-hand side. So on the left-hand side, I have ds dt, which is the rate of change. All right. And on the right-hand side, I'm going to get 4 pi because that's constant. And then I have r squared. What's the derivative of r squared? That's 2r. And then I have a dr dt. We do know that dr dt here is 2 centimeters per second. And we're trying to find this. All right. And we also know, of course, what this is happening when the radius is 8. So we know r is 8 centimeters. So taking all those things together, we get ds dt equals 4 times pi times 2 times 8 times 2. And what are going to be my units here? So this is surface area, so it's going to be centimeters squared per minute. I can also see that because I have 8 centimeters and I have 2 centimeters per minute. So I have here in purple, I have a centimeter and a centimeter times each other in the top. So that's going to give me a centimeter squared. And I have a minute in the bottom. And so I get a minute, still keep a minute in the bottom there. All right. So my final answer, I get ds dt is I multiply these things together, 4 times 2 times 8 times 2. Oh, let's see. I think that's 128. So it's 128 pi centimeters squared per minute. Make sure you understand the one we just did and also understand the one in the study guide. Interval of increase, decrease. All right, so what do we have here? Suppose I'm given this function. I'm going to use the same function that's on the study guide just because that's convenient here. Let's make sure I get this right. Okay, so what are the intervals of increase or decrease for that function there? Well, to find the intervals of increase or decrease, we need to find critical numbers, okay? And that's where the derivative equals 0. And then we make intervals, make a table of intervals. If the derivative is greater than 0, it's increasing. And if the derivative is less than 0, it's decreasing. So let's apply that to this problem here. So I've got my function f. The one we're going to use here is this. All right, take its derivative. I get 12x cubed minus 12x squared. And just as we mentioned here, we want to find the critical numbers. We want to set it equal to 0. So we set it equal to 0. To find the critical numbers, now I'm going to factor this. I'm going to factor the 12x cubed minus 12x squared. And to do that, I'm going to take out what's in common. So they both have a 12, they both have an x squared, and I'm left with an x minus 1. All right, and so what are my critical numbers? When do those numbers equal 0? Well, that implies x is either 0 or x is equal to 1, right? That means x is equal to 0, and in purple here, this means x is equal to 1. That's when we get 0 here. Okay, so now I make my table. We'll do this in black. I make my intervals. So I go from negative infinity to the smallest critical number, which is 0. Then I make one from that critical number 0 to the next critical number, which is 1. And then I don't have any more critical numbers, so then I take that one we just used and I go to infinity. And I make this table with 3 columns here. And then here's my function. And I'm just going to take a value in each of those intervals. So what's the value in the interval from negative infinity to 0? I'm going to take negative 1, and I'm going to plug this into my function. Um, I prefer to work with it in this form, where I factored out the terms in common. So I've got 12x squared times parentheses x minus 1. But you could use this one. Either one of these works. So when I plug that in, do the negative 1 here. I plug that into this function here. I see that I get 12 times negative 1 squared, which is a positive number. And then I have in the parentheses negative 1 minus negative 1 is negative 2. So I have a positive number times a negative number. It gives me a negative. It doesn't matter what the number is. We just want to know whether it's positive or negative. So that means it's decreasing on that interval. Now I do the same thing with the next one. I take a number in between 0 and 1. And here I'm going to have to take a half, but that's okay. And I'm going to plug it back into that red function there. If I put a half in for x, the 12x squared, that's going to be a positive number. And then I put in a half into the parentheses x minus 1. So a half minus 1 is a negative number. So positive times a negative is negative. So it's decreasing also on that one. And then last, I'm going to take a number here, like 2, that's in the interval from 1 to infinity. And so when I plug that into my function over here now, I'm going to get a positive number. So I have 12 times 2 squared, which is positive, and then I have 2 minus 1, which is positive. Positive times a positive is positive, so it's increasing. So it's increasing on 1 to infinity, and it's decreasing on negative infinity to 0, union 0 to 1, which also could be written as just negative infinity to 1. Okay, either of those is right from what we talked about in the book. Okay, and where are their local max and mins? Well, I look at this. If something is decreasing, like it is from negative infinity to 0, and then from 0 to 1, it keeps decreasing, there is no min or max in between them. But if I go now from 1 to infinity and it's increasing, that means I'm going to get a local min here. So this has neither max nor min there, but here I get a local min. So there's a local min at x equals 1. And if you wanted to find the y value, you'd go back to the original function and you would say, so f of 1. So that, again, my function was 3x squared. Let me just put it in here. So 3, okay, let me do that over. That's not very good. Okay, my function was f of x equals 3x to the fourth minus 4x cubed plus 2. So I want to find out what the value of the function is at 1 because that was my local min. And so now I put 1 in there for x and I get this. And that gives me 3 minus 4 plus 2 and that equals 1. So local min at x equals 1, y equals 1. Next problem here, concave, concavity, and inflection points. So let's do the same function. Remember we had f of x equals 3x to the fourth minus 4x cubed plus 2. And in the previous problem, we found out its first derivative was 12x cubed minus 12x squared. For concavity, we take the second derivative and do the same thing we just did. So I'm going to take the second derivative and I get 36x squared minus 24x. And like we did in the previous one, we set that equal to 0. So now I factor out what's in common. So they both have a 12 and an x, and then I'm left with a 3x minus 2 equals 0. So that tells me that x equals 0 from this one. And if I do this, this is 3x minus 2 equals 0. That gives me 3x equals 2, or x equals 2/3. So I get x equals 2/3. Those are my 2 points that I use now to make my intervals. So I have negative infinity to the smallest number, okay, which was 0, the ones we just got. And then I go from that number to the next smallest number, or which you could think of as almost like a critical number here, which was x equals 2/3. And then I do, that since that's the last one, I go 2/3 to infinity. Okay, and I look now at the second derivative here because we're doing concavity. And I do the same thing. I do a second derivative at a point in here. So I do -1, and I'm going to write down my second derivative function here in the form 12x times 3x minus 2. All right, when I put -1 into this function here, I'm going to get a negative times a negative. I'll get 12 times a -1, which is -12. Inside the parentheses, I have -3 minus 2, which is -5. So a negative times a negative is a positive. And when I have positives, that's concave up. Concave up. All right, then I take one in the second interval here, um, 0 to 2/3. It's not really nice, but it's what we got. So I'm going to take 1/3 as my number here. And I'm going to plug that in to again, my second derivative. So when I 12 times 1/3, it's a positive number. When I put 1/3 into the parentheses, 3 times 1/3 is going to give me 1. 1 minus 2 is -1. So I get a negative number there. So I have a positive times a negative. So that's a negative. So it's concave down. Okay, because it looks like that. And then finally, I can do my last one, the second derivative at 1 works there. And when I plug 1 in there, I'm going to get a positive and a positive. So I get that. So it's concave up. Concave up at or on this, concave down on 0 to 2/3. And what are inflection points? So inflection points are where it changes from concave up to concave down. So it's going to be at x equals 0 and x equals 2/3. And then I should figure out f of 0 equals something and f of 2/3 equals something. The 0 one's easy to figure out, but I'm not going to do that right now. And the 2/3 is a little bit difficult. That's why I'm not going to do it either. Okay, so there's a concave up, concave down. Another topic, L'Hopital's rule. So suppose we have the limit e to the 3x minus 1 minus 3x over x squared. Okay, I want to do that limit. So anytime I do a limit here, I'm going to do the substitution method first. I put in 0. When I put in 0, I get e to the 0 minus 1 minus 3 times 0 all over, I get this. And when I do that, e to the 0 is 1, so I get 1 minus 1 minus 0 over 0 gives me 0 over 0. And that's an indeterminate form, and I can use L'Hopital's rule. Notice I did this off to the side here. I didn't put it here in the problem. I'd recommend not putting it. I recommend doing it like I did it here, where I did my calculations off to the side. So now L'Hopital's rule says that I can take the derivative, that this limit, this original limit, is going to equal the derivative of the top, everything on the top, over the derivative of everything in the bottom. Don't use the quotient rule, but do it this way. All right, so what's the derivative of e to the 3x? Well, by the chain rule, the derivative of e to the 3x is e to the 3x times the derivative of what's in blue, which is 3. That's going to equal 3e to the 3x. if you had something like the derivative of e to the sine x, okay, what's that going to equal? It's going to equal e to the sine x times the derivative of the sine x, what's in the exponent, which is e to the sine x times cosine x, which might be written, another way to write that is this. Yeah, make sure you know how to take the derivative of e to any power. Okay, so I'm going to keep writing down my limits here. So I take the derivative of e to the 3x, that's 3e to the 3x. The derivative of minus 1 is 0. And then the derivative of minus 3x is minus 3. And that's all over the derivative of the denominator, x squared, which is 2x. And now if I do my substitution method again here, I'm going to get 0 in the numerator because I'll get 3 plus 0 minus 3. When I put e to the 3x, again, if I put in 0 there, that's e to the 0, that's 1. 3 times 1 is 3, so I get 3 plus 0 minus 3, so I get 0 on the top. And when I put 0 in for the denominator, I get 2 times 0, which is 0. So I could still do L'Hopital's rule again. So I now take the derivative, again, of the top. I'm going to leave off the plus 0, and I take the derivative of the denominator. L'Hopital rule says it still will work, so then I get the limit as x goes to 0. The derivative now of 3 times e to the 3x will be 9e to the 3x. And the minus 3 derivative of that is 0. And then the derivative in the denominator of 2x is just 2. Now when I do the substitution method, I'm going to get 9e to the 0 over 2. And this is 1, so I get 9/2 as my answer. Optimization problem here. Let me do the one that's in the study guide here. So you have I'm just going to read this one instead of writing it all out. You have a rectangular piece of cardboard. Yeah, that's 5 by 8, and the box, a box with an open top is to be constructed from the piece by cutting out a square of length x from each of the 4 corners and bending it up sideways, up the sides. Find the largest volume. Okay, so you have a piece of cardboard here. We're going to say this is 8, this is 5, and then you're going to put it in red here, little corners here that you cut out. Each of these is x. And when I do that, I can now make a new box by folding those edges up. It kind of looks like this, like that. And this length here is 8 minus 2x, because I have the 8 for the whole length, and then I have a minus x and a minus x here that you cut off. So this length here is x, 8 minus 2x. Likewise, this is going to be 5 minus 2x, and the height is going to be x. And you're supposed to find the value of the dimension of this so that it has the largest volume. So what's the volume of a box? That's one you should know. It's going to be base times height times length or width. So in this case, it's going to be 8 minus 2x times 5 minus 2x times x. If I multiply those together, I'm going to get 40 minus 16x minus 10x plus 4x squared, all times x. And so that's going to equal 40x minus 26x squared plus 4x cubed. And now I want to take the derivative of this. So the derivative of this, to find the maximum, I take the derivative, and I set it equals 0, find the critical numbers, and then see if it's a max or min. So I take the derivative of this, I get 40 minus 52x plus 12x squared. I'm going to take out what's in common. Looks like everything has a 4 in common. So, and I'm going to write this in order with the x squared first. So I'm going to have 3x squared. I take 4 from minus 52, that's 13x. And 4 from 40, that's going to be plus 10. I'm going to set that equal to 0. So I need to factor this. So I have a 3x and an x, and it's going to be a minus and a minus. And so two things that multiply to be 10 in this case. And then when I put them in here, I'm going to get 13. And I think it will be a 1 and a 10 here. And I can check that. This is going to give me a 3x. This a minus 3x. That's going to give me a minus 10x. I add those together, I get minus 13x. So that works. All right, so that equals 0. So that means x is equal to 1, or 3x minus 10 equals 0 from this part here. And if I solve for x here, I'm going to get x equals 10 thirds. All right, now we want to make sure that these numbers are realistic. Um, if I put these in here, remember I've got the side lengths of 8 minus 2x. Okay, so that's the, we'll just say length side. And we have a width of 5 minus 2x. If I put 1 in there, if x is 1, then length, this is L, is going to be 8 minus 2, which is 6, and width is going to equal 5 minus 2, which is 3. If x is 10 thirds, then length is going to be equal to 8 minus 2 times 10 thirds there, which I could figure that out. But we'll just leave it for now. It's a positive number, which is what's important. On the other hand, if I do width here, I've got 5 minus 2 times 10 thirds. All right, so that's going to be 5 minus 20 over 3, which is, if I get a common denominator here, I got 15 minus 20 over 3, which is negative 5 over 3. Can't have that. Can't have a negative width there. So the answer, x equals 10 thirds, is not possible. So that means we're just doing the case of x equals 1. Now, some of you may just say, well, okay, that's the answer, we're done. But really what you should be doing is taking the second derivative and figuring what the value of 1 is there. So um, remember the first derivative right here is equal to 40. Let's see, let me get this here. Is 40 minus 52x plus 12x squared. Okay, so I've got that. So then the second derivative is minus 52 plus 24x. And now I look at the second derivative of 1. I get negative 52 plus 24. And that is equal to, I think, what, negative 28. Doesn't matter really what it is. We know it's negative. What happens if I have a negative? Second derivative. Negative means I have the stormtrooper face or frowny face. And that means that this point here, the critical number, is a max. So we have a max at x equals 1. Make sure you do this because some people are concerned that they missed this on exam 4 because they didn't do the second derivative test there. Check that. And the question says, find the largest volume. All right. So what is the volume again? The volume formula, the volume was equal to, going back up here, it was this 40x. Let me just redo this over here. So volume is 40x minus 26x squared, I believe. Yep, plus 4x cubed. So volume when x is 1 would be 40 times 1 minus 26 times 1 squared plus 4 times 1 cubed. So that's 40 minus 26 plus 4. That's going to be 44 minus 20, 44 minus 26, which is going to be then 18. And what are my units here? Going back to it, it's feet. So it's going to be 18 feet cubed because I'm doing volume, and volume is 3 dimensions. So that's what it is. Make sure you answer the question. Sometimes they ask you what are the dimensions of it. And in this case, if they asked you what the dimension is, we figured that out earlier, right up here. The dimensions would be 1, 3, and 6. And we could check that. Now, if those are the dimensions, I'll multiply those together. 1 times 3 times 6 would give me the volume, which is 18, which is the same answer we got here. Let's skip antiderivatives because we had that not too long ago. But let me do the definition of the integral here because the students find this one a little bit more challenging and it's new material. And it's likely to be on the test because it's new material. Express the following, express as a definite integral. And let me explain, when you're given the limit as n goes to infinity of the sum I equals 1 to n, 4 over n times 1 plus square root of 2 plus 4i over n. Okay, so how do I do this one here? Let me look at some things here. Okay. So first thing I would do is I want to remember what the definition is. It says the integral from a to b of f of x dx equals the limit as n goes to infinity of the sum I equals 1 to n of 4, oh, sorry, let me erase that, of f of x sub I delta x, where delta x equals b minus a over n, and x sub I is a plus I delta x. For this to make sense, delta x represents the base of the rectangle. So we've got some curve here, and we're trying to figure out this integral, the area under the curve here. And what do? We make a bunch of rectangles. So we have a bunch of rectangles here. And delta x is the base of all these rectangles, okay? And they're all going to be the same length here. So we're taking like the total length here from A to B, and we're just dividing it into the number of rectangles we have, which is n. The x sub I is then the right endpoint that we get here. So how do we get the right endpoint? Let me pick a color that sticks out. So I remember I is 1 to n. So what is like the first one? X sub 1 is a plus 1 times delta x. So that means I'm starting here at the point A and I'm going one space over. So I get this. This is what x sub 1 is. And when I do f of x sub 1, it equals the height of first rectangle. So that's this point here. That's the height, and this is the base. And so when I multiply those together, I get the area. So this represents the area of a rectangle. When we do x sub 1, when we do x sub I equals 2, okay, I'll just do another one, x sub 2, then we're going to get a plus 2 times delta x. So that means I'm going to start here and I go over 1, 2 spaces. So I get this. So this is x sub 2. And I look at that height there, that's f of x sub 2 right there. And so this is going to be this now when I is 2 is going to be the area of my second rectangle. And because I'm summing these, I'm adding up all the areas of the rectangles together. And then as n goes to infinity, I'm getting more and more rectangles in there, so we get the area under the curve. Okay, so that's the definition of that. And again, let's see, we've got this function here. Let me do this in black. The limit, as n goes to infinity, of the sum I equals 1 to n of 4 over n, 1 plus the square root of 2 plus 4i over n. Okay, and I want to write that as an integral, and I need to figure out what a is, what b is, and what my function is there. Well, what do? I look at this, and I've got two terms. I've got this in the box, and then I've got this in the circle. All right. One of these is f of x sub I, and one of them is delta x. Well, I look at this one, the this one here, the 4 over n, is going to be the delta x. There's no i's there, so it can't be f of x of I. All right, so it's going to be that, and it has an n in the denominator. And we know delta x from up here. Okay, delta x is b minus a over n. So this tells me that b minus a equals 4. Now I don't know what a and b are yet, but I do know, so this is a, this is b, but I don't know what b and a is. I just know the difference is 4. So if that's delta x, then I'm going to get f of x of I is going to be this other part here, which is going to be 1 plus the square root of 2 plus 4i over n. Now, I need to look at this and say, I know that, remember that up here we had x sub I equals a plus I delta x. And we know that delta x from up here was 4n, so I got I times 4n. Okay, so we get a plus 4i over n. Well, I look at what I have over here in red. Let's do this red here. And I look at this, and I see this right here. This has to be my x sub I. And this would tell me that um, a 2 plus 4i over n is going to equal a plus 4i over n. So that's going to tell me that a has to equal 2. Well, the fact that we had earlier here in purple, b minus a is 4 and a equals 2, that means b is going to equal 6. All right, so so I know I'm going to have the integral from 2 to 6, and then I have my f of x dx, and I just need to figure out what is f of x at this point. And I go back here that I've got this here. So I've got f of x sub I equals 1 plus the square root of 2 plus 4i over n. But we know that from what we just did, that under the square root is the x sub I. So f of x is going to be 1 plus square root of x. So my final answer would be the integral from 2 to 6 of 1 plus square root of x dx. So the fundamental theorem of calculus says that you can differentiation and integration undo each other. So in this problem here, differentiate g of x, which is an integral here, then you're taking the derivative of g. So you're differentiating d dx of the integral. So that's the fundamental theorem of calculus. The book calls that part one because you're doing the integral first and then the derivative. Whenever you have one of these, all right, if it looks like this problem here is going to be one of these types of problems, it's going to be a function that's written as an integral, and you're going to have the variable up here, and this is down here is a constant, and then you've got these t's here, which are dummy variables. When you've got a situation like that, when you take the derivative, all it is by the fundamental theorem of calculus is I look at this part, which is called the integrand, and I replace my variable with this. So in this case, this is going to equal 2 over 1 plus x cubed, everything squared. Remember, I've got a square up here, so I've got to square that. And then I have to do, by the chain rule, I take the derivative of what I've inserted. So in this case, it's going to be 2 over 1 plus x to the sixth. And when I take the derivative of x cubed, that's 3x squared. And so that's more commonly written as 6x squared over 1 plus x to the sixth. That's my answer there. So look for those particular ones. That's a very distinctive type problem. The other type of problem, I'll call that was A. The B would be to do an integral, just say 1 to 2 of x squared plus 1 over x dx. All right, so when I do that, I don't know a quick way to do this. So I'm to find an antiderivative of this. So what we want to do here is we want to find the antiderivative of this part right here. Um, I don't know an antiderivative of that part I circled in red, but I can simplify it. So this would be x squared over x plus 1 over x dx. And so I can rewrite that as the integral from 1 to 2 of x plus 1 over x dx. And now by the fundamental theorem of calculus, I just find the antiderivative. The antiderivative of this is going to be 1 half x squared. And the antiderivative of this, it's 1 over x, so it's going to be natural log of x there. And because I'm given specific numbers here, I have to evaluate these for values x equals 2 to x equals 1. So when I plug those in, I get 1 half, then I plug in the 2, plus the natural log of 2, minus, uh, plug in the 1 for the x in these ones here. Okay, um, so then I have 2 squared, which is 4, and I have a half times 2, so I get 4 halves or 2 plus the natural log of 2. I can leave off the absolute value because I just want to make sure that what comes after the natural log is a positive number, but 2 is a positive number, so I could do that. And then I've got minus. Now I have 1 squared, which is 1. A half times 1 is a half, plus, and the natural log of 1. What's the natural log of 1? That's 0. So we can put down 0 there. And so I now have 2 plus natural log of 2 minus a half, or I've got 3 halves plus natural log of 2. Let's do a net change theorem here. So water leaks out of a tank at a rate of R of T equaling 200 minus 8T liters per minute, where T is between 0 and 25. Find the amount of water that leaks out in the first 5 minutes. So anytime you have a problem like this, it's going to be an integral. It's going to be the integral of R of T from the first time to the second time, dt. Um, and so in this particular case, it's going to be in the first 5 minutes. That means I start from 0 minutes to 5 minutes, and my R of t is 200 minus 8t dt. So now I integrate this one, and I get 200t minus 4t squared evaluated from t equals 5 to t equals 0. What I've done is I found the antiderivative. The antiderivative of 200 is 200t, and the antiderivative of minus 8t is minus 4t squared. When I say the antiderivative, that means if I take 200t and I take its derivative, I get 200. And likewise, if I take 4t squared there, I take its derivative, I get 8t. So that's that. So now I just plug in those values for t. So I have 200 times 5 minus 4 times 5 squared. And then I put in 0, which is really nice. I always like it when they have 0 here, because then things just become very easy to compute. 200 times 5 is 1,000. 5 times 5 is 25. 25 times 4 is 100. And then I've got 0 minus 0. And so that's just going to be 900. What's the amount? So it's going to be 900 liters because that's my units there. All right. Let me just end up, I'm going to do one more example. This is going to be a U substitution. We're supposed to evaluate the integral from sine x to square root of 1 plus cosine x dx here. So I need to do a U substitution on this one because I don't know the antiderivative of this one. So I look at what's the most complicated part here that would simplify things, and I'm going to let u be what's under the square root, 1 plus cosine x. Then I need to figure out what du and dx is. So I take the derivative of u, I get du. Take the derivative of 1 plus cosine x. Derivative of 1 is 0. Derivative of cosine is minus sine x dx. All right. And I look here, this part here is similar to this part here. In fact, I want to get to be exactly the same. So I'm going to take a negative over here. So I'm going to take this negative and put it over here. So I get negative du equals sine x dx. So when I substitute this in, my integral of sine x times the square root of 1 plus cosine x dx there, that's not there, is going to equal, what do I get? So when I put in the u here, I'm going to get a u under the square root here. So I get it under there. And for the dx sine x, that's this part here. So the sine x dx is going to be a minus du. So what I get is this integral of sine x square root of 1 plus cosine x dx equals the negative of the integral of the square root of u du, which is the same thing as the negative square root of u to the 1/2 du. Now I know what the antiderivative of that is. Um, so the antiderivative of u to the 1/2 is u to the 3/2, and then I multiply by its reciprocal 2/3, and I do a plus c. And then the last thing I need to do is substitute in what I have for u. U was 1 plus cosine x. So I need to put that back in and get a plus c, and there's that. Okay, that was really long. Sorry about that, but I tried to do as many problems as I could as a review. Hopefully you find this is helpful, and study for the exam and you'll do well. All right, thank you very much. This is Coach Dorf. Have a great day. Bye.